Hello students, here is another problem on a determinate beam and by the method of superposition. So determine all support reactions. E is constant, construct the shear and bending moment diagrams and sketch the elastic curve. So E is the given beam and the loadings. We have a fixed support at A. So that's why we use the area moment concept in solving these problems. So we will divide this trapezoidal loading into two parts. We have the rectangular loading of 18 kilonewton per meter, and for the triangular part, 36 minus 18, so 18 kilonewton per meter. So the moment diagram, due to the uniform 18 kilonewton load, just for portion AB, is 18 times 6 times 3, and that is 324 over EI. Then it is second degree. Then for the triangular load, 1/2 of 6 times 18 times 2 is 108 and it is third degree. So that's the corresponding curve. For this rectangular loading at B, 18 times 4 times 2 is equal to 144, but because the moment of inertia is 1.25 I, that's why we only have 115.2, which is 144 divided by 1.25, and it is a second degree curve. Now, as moment at B just to the left, it goes back to 144, so that's why we have 144 here. The equivalent loading of 18 times 4, which is 72 kilonewtons. So imagine you have 72 here at B. 72 times 6 is 432 kilonewton meter. So this is the moment due to the equivalent concentrated load of 18 times 4, which is 72. 72 times 6 is 432. Next, the moment of this 90 kilonewton meter load is supposedly 90, but because up to B, the moment of inertia is 1.25, so 90 divided by 1.25 is 72. Now, as we enter to portion AB, it goes back to 90, so that's why we have 90 here all throughout. Then for the last loading, which is this, we have 15 times 2 times 1, which is supposedly 30, but because the moment of inertia is 1.25, so 30 divided by 1.25 is 24, and it is second degree. But it lies outside portion ABC. Then 24 is extended up to here. Then because the moment of inertia is 1.25, as it enters AB where the moment of inertia is just I, it goes back to 30. Then 15 times 2 is 30. Imagine there is 30 kilonewton load at C. 30 times 8 at B. 30 times 8 is supposedly 240. But because the moment of inertia is 1.25, 240 divided by 1.25 is 192. As it enters AB, so that's why it goes back to moment of 240, and this is extended. Then remember the equivalent load of 30 for 15 kilonewton load. So 30 times 6 is 180. So 30 times 6 is 180. That's the portion when the 15 times 2, 30 kilonewton load is imagined to be transferred here because the moment is 240 divided by 1.25. 192 is already here. But actually, the moment of this load is 15 times 230 times 9 plus 5, 9 plus 6, 15. So 30 times 15 is supposedly 450. And 450 is 30 plus 240, 270 plus 180 is also 450. So that's the moment diagram by parts. We now compute EI, deviation of C relative to the tangent at A, and that deviation of C relative to the tangent at A is automatic delta C also, and it is expected negative when supports B and C are removed. So beginning with this area, because we have to define it as moment of areas between A and C with respect to C. So take note the reference is C. So the area is 1/3, second degree, 1/3 of 6 times 324, because this is 6/4 or 1.5. The distance of the centroid of this area from C is, because this is 14, 14 minus 1.5 is 12.5. So 1/3, 6, 3, 2, 4, 12.5. Moment of that area with respect to C. For the next area, 1/4 of 6 times 108. This distance is 6/5 or 1.2. The distance of centroid from C is 14 minus 1.2, so 12.8. So that's why you have here 1/4, 6 times 108 times 12.8. Next, for this second degree area, 1/3 of 4 times 115.2. This is 4/4 or 1. So the distance of the centroid of this area from C is 8 minus 1, so 7. So that's why you have 7 there. Then the moment of this rectangle, 6 times 144. The distance is 3 plus 8, 11. The moment of this triangle, 1/2 of 6 times 432. 1/2 of 6 times 432. This is 1/3 of 6, 2. So its distance from C is 14 minus 2, so 12. Then this rectangle here, the area is 6 times 72. The distance is 3 plus 2, so 5. 6, 72, 5. For this rectangle, 6 times 90, then 3 plus 8, 11. 6 times 90, 11. Then for this rectangle, up to here, moment is 8 times 24 times 4. Half of 8 is 4. So 8 times 24 times 4. For this rectangle here, 6 times 30, 3 plus 8, 11. 6, 30, 11. Then for this triangle here, 1/2 of 8 times 192, 1/2, 8, 192. This is 2/3 of 8. 2/3 of 8 is 16/3. And for this rectangle here, 6 by 240, 3 plus 8, 11. 6 to 40, 11. And finally, for this triangle, 1/2 of 6 times 180. Since this is 2 meters, 1/3 of 6. So this is 14 minus 2. 1/3 of 6 is 2. So this is 14 minus 2, 12 meters. So computing, EI delta C is negative 73,568.8 kilonewton meter cube. Likewise, EI deviation of B relative to the tangent at A is the moments of areas between A and B with respect to B. And it is also EI division of B relative to A. So that's why, beginning with this area, 1/3 of 6 times 324. The moment arm is 6 minus 1.5, 4.5. For the next area, 1/4 of 6 times 108. This is 6/5, 1.2. So the distance of centroid from B is 6 minus 1.2, 4.8. So 1/4, 6, 108, 4.8. Then for this rectangle, This is no longer included because we only consider AB. So 6 times 144 times 3, 6, 144 times 3. For this triangle, 1 half of 6 times 4, 3, 2, 2/3 of 6, 4. 1 half of 6 times 4, 3, 2 times 4. 1 half 6, 4, 3, 2 times 4. Then for this rectangle here, 6 times 30 times 3. 6 times, sorry, 6 times 90 times 3 for this rectangle. 6 times 90 times 3, which is that. Then for the next rectangle, 6 times 30 times 3. Then for this big rectangle, 6 times 240 times 3. 6 to 40 times 3. Then finally, for this triangle, 1 half of 6 times 180, 2/3 of 6, so 4. 1 half of 6, 180 times 4. So computing, EI delta B is negative 20,109.6 kilonewton meter cube. Then for the moment due to the reactions, so we have RB and R sub C. RB times 6, so we have 6 RB, that's 6 meters. Then R sub C at B, R sub C times 8 is 8 RB, supposedly, 8 RC rather, divided by 1.25, so that's why we have 6.4 RC. But just to the left of B up to A, it is 8 R sub C because originally R sub C times 8 is 8 R sub C. Then 8 R sub C times 14 is 14 R sub C at A because the moment of inertia is now I. So we divide this moment diagram of the reaction at C at A into these areas here when we consider portion AB and when we consider portion A to C. So EI delta CR is simply the moments of areas between A and C with respect to C. So take note that C is here, 14 meters from A, from the left. So the moment of this area is 1 half of 6 times 6 RB. And since this is 1/3 of 6, 2, 14 minus 2 is 12. So that's why the moment arm is 12 for that area. Then plus the moment of this area, 1 half of 8 times 6.4 R sub C. 2/3 of 8 is 16 over 3. Then for this area here, 1 half of 6 times 14 RC. And the moment arm is again 12. 14 minus 2 because that is 2. So 12. And finally, this area here, 1 half of 6 times 8 R sub C. The moment arm is 2 plus 8, so 10. Combining like terms, EI delta CR is 216 RB plus 13,208 over 15 R sub C. So therefore, EI delta CR is equal to the absolute value of EI delta C. So 216 RB plus 13,208 over 15 R sub C equals, supposedly plus EI delta C equals 0, but when we transpose EI delta C to the right, it becomes positive. So equals 73,568.8, call that equation 1. EI delta BR, so we only consider moments of areas between A and B with respect to B. So we have 3 areas to consider. All are triangles. For the first triangle, 1 half of 6 RB times 2/3 of 6, 4. Then for this area, 1 half of 6, 14 RC, 2/3 of 6, 4 again. Then finally, for the moment of this area with respect to B, 1 half of 6, 8 R sub C, then 1/3 of 6, 2. Combining like terms, EI delta BR is 72 RB plus 216 R sub C. Therefore, we can formulate the second equation, 72 RB plus 216 RC is equal to this value to the right, 20,109.6. So solving equations 1 and 2 simultaneously, we obtain RB 108.486 kilonewtons and R sub C 56.938 kilonewtons. Then when we consider BCD to solve for moment at B, so this is the positive assumption of direction of moment at B, so that the shear at B is not involved. We sum up moments about B. So MB plus moment of this load 18 times 4 times 2, then plus 90 plus 15 times 2 times 9, 15 times 2 times 9 equals moment of the reaction R sub C 56.938 times 8. So the moment at B is negative 48.496. And take note of that when we construct the shear moment diagrams later. Then, considering the entire system, summation forces Y equals 0. So RA plus 108.486 RB plus RC 56.938 equals the area of this trapezoidal loading 1/2 of 36 plus 18 times 6 plus area of this rectangular loading 18 times 4 plus area of this rectangular loading 15 times 2. So solving for RA is 98.576 kilonewtons. Then let's now have the moment at A also considering AB. So summation moment about A equals 0. So summation moment about B equals 0 because we don't want to involve shear just to the left of B. We cannot use RB also because we cut B and just to the left. So RA is involved. So we have MA plus RA 98.576 times 6, RA times 6 is equal to moment at B, which is negative 48.496 plus the moment of this rectangular load 18 times 6 times 3, 18 times 6 times 3, then plus the moment of the triangular load 1/2 of 6 times 18 times 2/3 of 6, 4, which is that. So moment at A is negative 99.952 kilonewton meter. So take note of these values. Let's now construct the shear moment diagram on the next slide. So this is now the construction of the shear moment diagram. So we have the shear diagram in kilonewton, moment diagram in kilonewton meter. So first, these are the reactions, support reactions. So we go up 98.576. So that's why you have here 98.576. And then minus the area of this trapezoidal loading, 1/2 of quantity 36 times 18 times 6. So we have negative 63.424, then plus 108.486, so 45.062. 45.062 minus 18 times 4, loading here, so negative 26.938 from here up to C, constant, then negative 26.938 plus 56.938 is 30, then 30 minus 15 times 2 is 0. So that's the shear diagram. Then before we proceed to the moment diagram, construction of the moment diagram, we need to know the distance of this point of intersection with horizontal where shear is 0 from the left support so that we can compute area 1. And that's the shear. So imagine that this is the total intensity W, and we isolate this triangle here. So therefore, this is W minus 18, this part only up to here, W minus 18. So if that is x1, this is 6 meters minus x1. And this is 18 kilonewton per meter, 36 minus 18. So from the figure, W minus 18 as to 6 minus x1 equals 18 as to 6. 18 over 6 is 3. So W is equal to 3 times quantity 6 minus x1, transpose negative 18 to the right, so plus 18. Combining or simplifying, 3 times 6 is 18 plus 18, 36. So therefore W is 36 minus 3 times x sub 1. We can now set up the shear equation in AB. It is equal to 98.576, which is this, minus the area of this trapezoid, which is minus 1/2 36 here, W here, W is 36 minus 3x1, and this distance is x1. Simplifying, it is shear in AB 98.576, 36 plus 36, 72, divided by 2 is 36, so negative 36 times x1, then negative 3 times negative 1/2 is 1.5 x1 times x1, so 1.5 x1 squared. So we equate it to 0 because we want to find this point where shear is 0. So solving for x1, there are two roots, but this is the realistic value of x1. The other root is absurd. It goes beyond 6 meters, so this is the only value, possible value. Therefore, area 1 is the area of the shear diagram here, which is shear times dx1. So shear equation, which is this, times dx1, limit 0 to 3.15225, so it is 147.537 kilonewton meter. Then area 2, which is expected negative, is area integral of the shear equation dx1, and the limits is now from 3.15225 to 6, and it is negative 96.081. The rest of the areas can be solved. This distance, by the way, is 45.062 divided by 18 uniform load, or by similar triangles, you'll get 2.5034 meters. Therefore, this is 4 minus 2.5034, 1.4966 meters. So the area can be easily computed. 1/2 of 2.5034 times 45.062, that's the area. This is 1/2 of 1.4966 times negative 26.938, that's the area. The rest can be easily computed. So we are now ready to sketch the moment diagram. Remember, the moment at A is negative 99.952, negative 99.952 plus area 1, which is 147.537, and that is positive decreasing, 47.585. 47.585 plus area 2, which is negative 96.081, negative increasing, so we have negative 48.496. And remember, the moment at B is negative 48.496 from the preceding slides. And then negative 48.496 plus 56.404, positive decreasing, 7.908. 7.908 minus 20.158, negative increasing, negative 12.25. Negative 12.25 plus negative 26.938 times 2, up to here, the area of this rectangle. So negative 12.25 minus 26.938 times 2, negative 66.126. Since there is a couple load there, plus 90, negative 66.126 plus 90 is 23.874. 23.874 minus this area of the rectangle, which is 26.938 times 2. So you'll have negative 30, constant slope, decreasing, negative 30.002. Then finally, plus the area of this triangle, 1/2 of 2 times 30 is 30. Negative 30.002, positive decreasing, horizontal tangent here because 0 load here, 0 shear here is 0. So this is the moment diagram, and we project this upward, the points of inflection or points where concavity changes direction, here and here. So in this portion, we have negative concave down, elastic curve. This portion, positive moment, concave up. Then from here up to here, concave down through the support. Then we have positive moment, so concave up again. Then negative up to here, concave down. Then we have a positive portion here, concave up. And finally, negative moment, concave down up to the. So that's it. That's the elastic curve for this beam. The video is lengthy, so I'll stop. I hope that you were able to follow the explanations and the solutions.